Alright everyone, welcome back to the YouTube channel. I am Xavier Smith, and today I'm going to finish Unit 6 of AP Statistics. This is Unit 6, Part 2, which has to do with two sample z intervals for a difference of proportions, and two sample z tests for a difference of proportions, which are like the same thing as one sample, but they just have two. And then we're going to go over some power, just some rules about power, like how to increase power, how to decrease power, how to decrease type 2 error, how to increase type 2 error. Okay, so let's just start. We've got one example on two sample z interval for difference of proportions, then one example on two sample z test for difference of proportions, and then we have power. Okay, so let's just do it. It's basically the same thing. Okay, so the question: 800 randomly selected US adults in 2001 were interviewed. 66% had seen at least one movie in a movie theater during the previous year, compared to 39% of US adults in 2021 in a random sample of 811 US adults. Okay, calculate and interpret a 95% confidence interval for P 2021 minus P 2001. Okay, so first we have to state what we're doing, right? And it'd be helpful to say like 95% CI, like confidence interval, and then you say two sample z interval for like difference of proportions P 2021 minus P 2001. You say difference of proportions P 2021 minus P 2001, and then you say, then you have to give context. P 2021, I'm going to give this quickly. Proportion of US adults, or I'll try to give it quickly. US adults in 2001, in 2021. In 2021, that saw at least one movie in movie theater. At least one movie in movie theater in past year. And then you're probably going to want to write this out again. I forget the other way to do it, where you basically say them both in one. But then you'll say P 2001 equals proportion of those in 2001, like those US adults in 2001. And I'm just going to draw an arrow here for simplification, but you just write it again. That saw at least one movie in movie theater in past year. Okay, boom. Okay, so now we stated all we need to do. Now we need to check. All right, so again, it's 10%, random, and large counts. Okay, so 10%. Now, instead of just doing like NP is greater than or equal to 10, we have two samples. So we have to do N1P1 is greater than or equal to 10. N1 times 1 minus P1 greater than or equal to 10. This is for the first sample. And then N2P2 is greater than or equal to 10. And 2 times 1 minus P2 is greater than or equal to 10. Right? And now we just say, okay, number of successes is greater than or equal to 10. We could write these down like 800 times 0.66 is greater than or equal to 10. Then this is for the 2001 up here. 800 times 0.34 is greater than or equal to 10. And then this one, 811 US adults, 811 times 0.39 is greater than or equal to 10. 811 times 0.61 is greater than or equal to 10. Okay, so we have large counts. You can plug that in your calculator. They're all greater than or equal to 10. Random is next. Random. And it's just random sample. So I'm just going to say SRS, simple random sample. Check. Oh, that wasn't even 10%. Sorry, that was large counts. I'm just going to say that's large counts and get rid of this 10% here. And then 10%, again, you need two 10%. So you say 800 is less than or equal to 0.1, like all U.S. adults that saw all U.S. adults in 2001. And then this will be 811 is less than or equal to 0.1 all U.S. adults in 2021. Okay, now we've got everything, and of course we're running out of room already. Great. Okay, now we do, or calculate, whatever you want to call it, which we'll grab our little p hats here. So I'm just going to write down, I'm not even going to write down, okay, general formula here for confidence interval, again, is statistic plus or minus margin of error. Well, this is point estimate plus minus margin of error, which is the same thing as, instead of just p hat here, we are doing p hat 2021 minus p hat 2001. And it's a p hat because it's our statistic. So p hat 2021 minus p hat 2001 plus or minus z star, and then you can put the little confidence there, like 0.95 to let them know. And then times standard error, which again is the root of, oh, this one's weird. It's like root, so it's usually p times 1 minus p over n, but now there's p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. So let's write that. That's a little bit of a mouthful. It'll be p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. And this formula should be given to you on the AP test, so you don't have to memorize those. And then you plug in, which we are going to run out of room here, but you know, whatever. I'll show you how to do it on your calculator as well. So P 2021 is 0.39 minus 0.66 plus or minus the z star of 95% is 1.96. Then root P1 is 0.39 times 0.61 over that would be 811 because the 0.39 is in the 2021. And then plus 0.66 times 0.34 over 800. All right, and then you could put that in your calculator, or again, you do have to show all this work to get credit, but again, you could just put everything in your calculator at the start. Okay, so I believe we go to stat, over to tests, and then it will be 2 proportion z interval. Yeah, which is B, 2 proportion z interval. And then we plug in, okay, x is, what is it? It's 66 out of 800. So we actually have to look this up now, which I'm going to write down. So 800 times 0.66 gives us 528. Because we can't just use the percentage, we actually have to use the number out of 800. And then 39% of 811, so 811 times 0.39 is 528. So I'm going to just say 528, 317. I'm going to round that up. Okay, and then I'm also going to do 811 minus 317 and just get that on the board. Goes to 494. 800 minus 528 is 272. Again, it's kind of hard when they give you these proportions. It makes it really easy to do this math and put in your calculator, but just doing this is easier for me than doing all that. But again, my rounding is going to be a little different than whatever the actual answer is, because instead of like 316.2, I said 317. Round it up. So again, 2 proportion z interval, and then we are going to have 528. I didn't even need those side numbers. That's my fault. 528 out of 800. And then that's not even x1. sorry. Since I just did 2021 here, but we're actually starting with, no, I did 2001, but we're starting with 2021. So 2021 was 317 adults out of 811, and then 2001, which we're subtracting by our P2, is 528 out of 800, and then our confidence level is 0.95. And again, we just click it and we get everything. We get P1, P2, whatever, and we get the interval. Okay, so now we get the interval, which is negative 0.0316, comma negative 0.22. And again, to conclude, to interpret, I'm not going to write it down, but you say we are 95% confident that the interval from negative 0.316 to negative 0.22 captures the true difference of proportions, and you'll put in parentheses P 2021 minus P 2001 of adults like those in the study in 2021 versus those in 2001 that saw a movie in the past year. You might have to replay that and listen to it again, but it's kind of weird. It's the same interpretation as before, but instead of just saying like the true proportion, you say the true difference in proportion of these, and then you give like in what way you subtract, and then again you just give context saying like of those in 2021 versus those like those in the study in 2001 that watched a movie in the past year. So you give context, but it just throw in a little verses there and you'll be all right. If you say anything like that, you're probably getting credit. You just have to be able to somewhat interpret it. Okay. Next, the Z test. Okay. Our question. Of 170 drive-thrus at Wendy's, 145 were accurate. At McDonald's, 139 of the 160 drive-thrus were accurate. Is there convincing evidence of a difference in the population proportion of accurate drive-thru orders at McDonald's and Wendy's? So again, whenever we have a test, we have hypotheses. So our hypotheses here, if we're just going to write down, our HO is just like what we're basing it off of. And what we're basing this thing, like, is there a difference? We're basing it off of there is no difference, right? That's our expectation. There is no difference, and we're trying to prove that wrong. So this would be like P1, or we'll say P Wendy's minus P McDonald's equals 0. This is basically just saying P Wendy's equals P McDonald's, like the proportion of each that is accurate is the same at both restaurants. So you're just saying PW minus PM equals 0. We just say it like this, but you could also say PW equals PM. The proportions of both are the same. And then HA, we're trying to propose that there is a difference in the population proportion. So it didn't say like, is Wendy's like have a greater chance of messing up an order? And it's like, no, right? It's just saying, is there a difference? So you'll say, okay, PW minus PM is not equal to 0, meaning there is a difference. Okay, and then you could also say PW is not equal to PM. They're the same thing. Okay, and now you have to say, like, this is the state part of it, and we're going to say to sample Z test for difference of proportions, and then you'll say like PW minus PM, and you say PW equals proportion of orders of drive-through orders correct of drive-through orders correct at Wendy's. And then you'll say PM equals proportion of drive-through orders Correct at McDonald's. Correct at McDonald's. Okay. Now, we've stated everything, and now we get on to the next part. I should probably have added an alpha level here. Since we're not given an alpha level saying it's statistically significant, we always just assume alpha equals 0.05. That's just a safe significance level. So throw that in your state. Okay, now check. The checks are always the same, unless, which I haven't shown you, an experiment. If you have an experiment, you don't have to do 10% condition, because like they're usually volunteers for experiments, and they're not pulled from a larger population. So therefore, 10% is just not applicable, and you just don't do it for experiments. It just can't be like generalized to the whole population of like people. It can only be really generalized to the volunteers. Okay, now check. 10%. Oh my gosh, everything is running out of ink right now. 10%. So just 170 is less than or equal to 0.1 all Wendy's drive-thrus. Wendy's drive-thrus, which we can assume to be true. We assume there's more than 1,700 drive-thrus at Wendy's. That's fair to assume. Okay, and then 160 is less than or equal to 0.1 all McDonald's drive-thrus. Okay, now we can just say random, and there's simple. I didn't put it in this equation, but like I didn't put it in the problem, but it is random. This was a big problem, and I always just take like little snippets of the information, but they were random drive-thrus at random places. So yes, it was a simple random sample. So check. And again, large counts, we have to do with two things, like with these two samples. But actually, when you have a two sample Z test only, you are going to do something that you don't usually do. So instead of using like P1 and N1 and P2 and N2 for large counts and finding your standard error, you're actually going to use what is called P hat C, which is really just the combination of like the total successes, like divided by the total amount of trials. So it's just like the average success rate, which would be P1 plus P2 over N1 plus N2, like the proportion of successes. Actually, these would be X's, saying like number of successes. So number of successes of the first plus the second divided by the number of trials of the first and the second would be, I know it's weird that you have to use it just for this, but I know 139 plus 145 over 170 plus 160. 160 equals, it makes a little bit more of the calculations easy, but honestly, I don't like it that much. This would be 284 divided by 330, which is approximately 0.861. I actually just don't want that 1 there, if that's fair, for my own sanity. Okay, so we're just going to say this is equal to 0.86. Now we have to say, okay, 170, like this is the N1 times P hat C times 0.86 is greater than or equal to 10. Yes. Then 170 times 1 minus P hat C is 0.14 is greater than or equal to 10, which is yes, because 170 times 0.1 is 17, so I know that times 0.14 is greater. And then 160, that's supposed to be a sixth, times 0.86 is greater than or equal to 10. Yep. And then 160 times 0.14 is greater than or equal to 10. And if you wonder what that was, this was N1 P hat C is greater than or equal to 10, and 2 P hat C is greater than or equal to 10. N1 times 1 minus P hat C, C is greater than or equal to 10, and then N2 times 1 minus P hat C is greater than or equal to 10. So yeah, instead of just using like P1, P2, you just use P hat C. Might make it simpler, might get confusing. Really, it could be either. Okay, and now do, and again, I'm not going to be able to conclude on this thing, so I'm going to have to read out the conclusion to you. Okay, so now the do section, our favorite, right? So again, this is basically, again, we said it's a z-test, so the general formula is the same for like a z-score, which is statistic minus parameter over standard error, which is the same thing as the statistic here, again, is not just p hat anymore. It's p hat 1 minus p hat 2, which is p hat w minus p hat m. So p hat w minus p hat m minus the parameter, which our parameter is really like PO or whatever they mean by that. It's just HO. It's PW minus PM without that little hat. And that will always here simplify to 0 because our parameter is always saying that the difference is 0 and we're trying to prove it wrong, right? So this is always 0. But we kind of have to write out PW minus PM for specific formula reasons for no reason at all. Most reasonable crash out, honestly. Okay, and then over standard error, which this one is also weird. So again, instead of using P1, P2, we are going to use P hat C. So it's P hat C times 1 minus P hat C times 1 over N1 plus 1 over N2. And I think this is also on the AP test given to you. And this is the same thing as P hat W. P hat W is 145 out of 170. 145 out of 170. 0.85. 0.85 minus 139 out of 160. Out of 160. 0.87. I didn't realize how close they were. 0.87 divide, and then this would be minus 0 because this is HO, which is again equal to 0. PW minus PM equals 0. PW minus PM would equal 0 over the root of P hat C, which is 0.86. 0.86 times 0.14 times 1 over N1. Our N's are 170 and 160. 1 over 170 plus 1 over 160. And then again, I ain't doing all this work, so I'm going to show you the calculator shortcut. All right, let's do it. So again, we go to stat and over to tests, and we're going to go to 2 proportion z-test. All right, 2 proportion z-test. And then our x1 is, again, our Wendy's, which was 145 out of 170. So 145 out of 170. And then our x2 was our McDonald's, which was 139 out of 160. 139 out of 160. And we're saying PW is not equal to P2. And then calculate. And we get our z-score, which you can use on your graph. And then this little p here with no subscript is your p-value, which you compare to your alpha value. Okay, so let's put this all down. So again, on our normal distribution, which for some reason we have to draw, our middle point would be 0. Like the difference of them is 0. And then the actual point we got was, where's the point we got? Oh, 0.85 minus 0.87 would be negative 0.02. Right? Yeah. So that would be the difference that we got here. And then again, this would be just like a left-tailed. This would be it's less than 0 would be our HA. But since it's not equal to 0, we're saying that the probability is the same on the other side. So we're saying negative 0.02. The chance of it happening on this side is the same as the chance of it happening on this side. So it's 0.02. We also have to fill in. And these p-values are the same. Like the proportion, the area under both these curves over here are the same. So when we said our p-value was 0.679, p-value equals 0.679, it really said that, oh, I probably should have put the z-score down. You would just throw the z-score there somewhere just to say it, but I clicked off of it. 0.679 is the addition of these two equal parts. So if you divide it by 2 and you just wanted to find like what's the area under one side of it, you just divide by 2 and get 0.339. Really 0.34 is the area under this curve. Okay, so since our p-value, this is interpreting without writing down. So because our p-value of that should probably be a 0.0679. I've never seen a 0.679 p-value. Since our p-value of 0.0679 is greater than our alpha value of 0.05, we fail to reject HO, and we have we fail to reject HO, and we do not have convincing evidence of, you can literally just state this again, of a difference in the population proportion of accurate drive-through orders at McDonald's and Wendy's. It's so simple now, and I didn't realize it before, that when you're stating context at the end, you can basically just pull the question, like difference in population proportion, all the way to the end and just paste it down there. You just rewrite it. I wish you could just draw an arrow as context, but for some reason, you can't. Sadly. Okay, I hope that made sense. And now let's go on to power. Yay. Yay, my favorite. I love power. Okay. Power. All right. So just a couple things. So if the number of people in the sample goes up, the power goes up, and therefore type 2 error goes down. Because whenever power goes up, type 2 error goes down. And the reason for this is because having more people gives you more information about the data set. Power is correctly rejecting HO when HA is true. So having more information about the data set will make you more likely to correctly reject HO when HA is true. You just have more data, so you're more likely to get the correct outcome. Okay, if the alpha level goes up, then the power goes up and type 2 error goes down. And the reason for this is alpha level, your significance level, is like the 0.01 significance level means that like the probability of something happening has to be less than 0.01, like happen less than 1% of the time for you to reject HO. But then a 5% significance level, it has to be less than 5%. 10% significance level has to be less than 10%, like happen less than 10% of the time. So compared to a 1% significant level, at a 10% significance level, you are going to reject things a lot more. Like if something happened 8% of the time, you're going to reject it at a 10% significance level, but you wouldn't at a 5% significance level. So here, you are just more likely to reject things all over the board. So therefore, you're more likely to reject things when, like, you're more likely to reject HO when HA is false, because you're just more likely to reject in general. But then this is also leading to type 1 error increasing, where you falsely reject HO when HA is not true. Okay. And then null and alternative hypotheses are further away. Power goes up, type 2 error goes down. And this is because since like these values that you're looking at are further away from each other, you're like, assume that the true difference is 0. Well, like if HO is like they're equal to 0, like the difference is equal to 0. But then in the power thing, you're given that the difference is like 0.05, then since it, like the further you get away from like what you're trying to prove it's not, the more likely you just are to reject, because there's less of a chance of it happening because it's just further away. Like if the HO was the difference is equal to 0 and HA, well, you were given in the power thing that it's equal to 0.01, right? You're not going to reject it very often because you could get a difference of 0.01 any day. but you're not going to get a difference of 0.15 any day. That's a big gap, right? So the bigger the gap, the more the chance you're going to reject it, like all over, like anytime. So therefore, the higher the chance you're going to reject it when HA is true, and therefore type 2 error goes down. And then when standard error goes down, power goes up, and type 2 error goes down. So this is the only one that when it goes down, power goes up. And I kind of relate this back to the number going up, like the number in the sample. Because really, standard error is like the root of P1 times 1 minus P1 over N1, basically. So when standard error goes down, it's probably N, like increasing. Because when N increases, standard error decreases, I believe. Yeah? Maybe. So when N increases, standard error decreases. So it's kind of saying the same thing here. When standard error decreases, power goes up. And again, you could memorize these relationships saying like, well, when alpha goes up, you're more likely to reject everything. So power probably goes up. Or you could just memorize N up, power up, type 2 error down. Alpha up, power up, type 2 error down. Further apart, power up, type 2 error down. Standard error down, power up, type 2 error down. And then again, it's like if N went down, power goes down, type 2 error goes up. And same thing, you could just flip the signs. Okay, well, that was my little thing for the day. I hope you guys enjoyed, and I hope you learned something today. All right, well, I will see you in the next one.